because we have particles which are falling, so which are not exerting force on balance and balance measures first the force exerted on it. So these particles do not exert the force on the balance. That's why we have a pitch along. But at the end, we saw that we had an increase to the higher, and that's because these rings, when they are touching the bottom, they are exerting a force which is caused by their kinetic energy gained by the bottom. Well, let me show you that. Let's see. Because, at the beginning, we have the elastic collision. Then that's why 1 and 2 should be conserved, and the energy should be transferred, and that's the reason why balance relation. Let's see how we reach this formula. Here, FC is representing the short pipe, and G is the gravitational constant, H is the height of the viscosity, and grain is maximum grain. And here we is the velocity of the grain just at the moment when it's reached the bottom, just at the touching time, and delta T is the duration for this dissipation of energy. It's not the falling duration, but it's just a time during which it transfers its energy. Yeah. So let's see what can be the parameters affecting phenomenon. The height. So the distance between the two compartments, the orifice diameter of our hourglass, and our grain density, the angle of the upper compartments mainly, and the top mass and flow would affect this. So let's see. We did our experiments with different heights and different diameters of orifice and different diameters and different angles and different densities of different materials. So let's see a video of our experiment. So let's see our results, for our experiments, which are targeted to consider density, we had the upper peak, which was increasing as a line. Lower peak is as stated in the formula. And here we see that we mainly have the difference between the plateau, which was after the lower peak, is approximately generally higher than 0. When we see the graphics interaction of our diameter, we see that when the orifice diameter increases, the aperture increases too. And our peak too. We see that the lower peak, the amplitude of lower peak increases in function of height, as expected with the formula. We see that when we increase total mass and flow, the upper peak speed is higher, in fact, starting mass. Here, unfortunately, points are not very current. Although we can see examples like that. So, what you can conclude here is that the lower peak and the upper peak in our graphics are actually increasing in maximum magnitude, height, orbit density different, and total mass as well. And we thought that the difference between reflection and initial value should be higher than 0, but unfortunately in our experience we couldn't see such a difference, which you will see in our graphics, which actually we couldn't conclude well. We thought it should be higher, unfortunately. Probably due to the errors in our experiments, we couldn't conclude well with the graphics, which were understanding the difference of the mass between the initial value and the plateau difference, as you can see here.
Thank you very much for your report. Can I just ask a couple questions? First, do you assume that your collision is perfectly inelastic? So when the sand hits the bottom, do you assume that it's not there? Yes. So do you include the sand bouncing off, or do you assume that it's not when it's the bottom?
Well, actually, yes, but it takes a time to transfer its energy. There's a time to transfer.
So for the digital scan, do you have an estimate for the response time? Because I noticed that you had like...
Yeah, unfortunately we had some problems with that, but we were using animations,
right,
so we don't have...
do you know how long the response time is? Like the delay between each time which the scale changes?
Well, actually it's really dependent on this.
I don't think you mentioned this in your experiment. Could you explain how you started your experiments? What was your reason?
Actually we used bottles.
Right.
We have bottles like that.
Yeah.
We put here and we made a hole here, and we put a stretch here. It was really tightly placed, and then we were burned stretch with everything.
Okay. So regarding how you change the density, you change the particle size, right?
Yes.
So you also pointed out that particle size was an important parameter.
No, I didn't put out that particle size.
So particle size is not important?
It's important, but in our case, it's strange.
Okay. And do you have any explanation for why you have the why you're expecting it to be above 0 at the plateau?
Particles are followed. We assume we actually cover them.
Okay, that's okay. We can talk about this in the discussion. My final question is, your hourglass is open to the air, right?
Yeah.
So how do you compare this to an actual hourglass which is sealed?
Yeah, actually in an hourglass there is some blackness by the pressure equalization.
Okay.
I suggest you discuss the
is number T.
Good morning, jury. I'm the opponent from Team Taiwan for problem number 13, weighing time. So before we go into a discussion on their report, I'd first like to remind ourselves of what exactly the problems they asked us to do, since they did not explain that very clearly in their report. So the important part here is that we examine how the hourglass changes its weight as measured by a scale. Meaning, essentially, what we're looking at here is not really the mass, rather the normal force exerted by the scale, because we know that scales measure normal force and not the mass of the object itself. So from this, then we need to look at this phenomenon and investigate the relevant parameters. So the opponent would like to propose this structure in order to actually completely solve this problem and answer the question. First, we need to know what is the mechanism that causes the weight change. Now, although they did have some explanation for the beginning part and the last part, the opponent thinks that they could do a much better job of explaining the middle plateau, which they said should be above zero. Next, we need to look at how properties of the hourglass affect the problem. So instead of looking simply at their experimental data, it is important that we actually examine what are the expected results from these parameters. And finally, we need to look at how we can predict very small and time-dependent changes. And for this we'll discuss how they can improve their experimental setup. So in terms of some strong and weak points of the reporter's report. First, a strong point, they gave a clear explanation of how they wanted to model the phenomenon. And they showed, they clearly did a lot of experiments on different relevant parameters and showed the graphs for us to see. And they cited their references. However, they do have a lot of places that need to be improved. Obviously, their experimental setup was quite problematic because they're using a digital scale. The response time is very limited, and so as a result, they could not have seen very small time-dependent changes. And regarding their theory, we think it is slightly too simplified, and there might be some errors in the math that we need to clarify later on. And regarding their graphs, because they have no comparison between the theory and the results, we can't be sure that their graphs regarding the parameters' effect on the phenomenon have any physical meaning. So for the discussion, these are the main points that we'd like to talk about. First, we want to know the mechanism for the measured weight. So as we stated earlier, the scale measures the normal force, and we want to clarify how that fits into their theory. And we need to know what exactly are the forces involved. Now, the opponent would also like to suggest perhaps a more analytical approach by examining the center of mass rather than looking at the forces, seen as trying to measure some of the variables in their equation. For example, the impulse time are pretty much impossible. Then we'd like to look at what exactly the effect of these parameters are, since they do not explain very clearly what each of these parameters would do. For example, the height, which we should expect to see a square root curve, they do not do any kind of fitting, and so we think that they could do a better job explaining that. Regarding the shape of the hourglass, the opponent really isn't clear as to why that is important. For that needs to be clarified further by the reporter. And for their predictions, we clarified that they are not actually considering the difference between an inelastic and elastic collision. and they don't consider different variables such as the changing flow rate or perhaps the air pressure inside the upper and the bottom parts of the hourglass. And finally, regarding their measurement, this one actually improved in terms of their experimental setup. First, the release mechanism seems to work fine, seen as burning minimizes the outside disturbances on the scale. However, the sensitivity and response time of the digital scale that they were using is questionable, and because of that, we think that they can improve on this part. And finally, because they were using an unsealed hourglass, we want to clarify that this can really be compared to a sealed hourglass, in which case air pressure becomes important and the flow rate may not be constant. And so with that, we want to enter discussion with the board.
Please start the discussion.
So regarding the mechanism and how exactly the scale measures the weight, could you display your theory slide? Okay, so in your theory slide, you try to calculate the force of a single particle of sand. Correct?
Yeah.
So I think actually, because you have a large group of sand, then in fact you can kind of ignore the time in which it collides with the bottom. So actually, do you agree with me? If you calculate the flow rate of the sand times the velocity at the bottom, then that will give you the impulse at the bottom. So if you assume that it's perfectly inelastic collision, right? So then the force is your momentum, right? Right. So in that case, the momentum of the sand particles as it hits the bottom would be your flow rate times your velocity at the bottom. Does that make sense? Okay. Sorry, can you go to the slide that has the equations on it? Yes. So here you see you have your velocity here, and you have your mass over here. In fact, you can just replace this term with the flow rate. So in that case, what do you expect? What do you see when you increase the flow rate?
When we increase the flow rate,
Yes.
then you mean the increase?
Yeah. You would get bigger effect. And it should be a linear relationship based on this equation here.
Yeah, actually, I think there's been a misunderstanding that that's the velocity of the bomb at the moment when it's
When it comes to the bottom, right? Yes.
And that's
Yeah. Same here. This is the velocity when it reaches the bottom. And so with this, you can actually simplify this a bit. And the second part here is this term here. Can you calculate this at all?
actually we try to do it by images, but we can do it by help
Yeah.
to our
Right.
yeah,
Okay.
to balance errors.
So in that case, I think that working with this question makes more sense. And in fact, you can actually calculate the velocity. So we can do that calculation from the equation.
Again, we work with our radius, and the radius we have some parameters.
I mean the velocity of a single ray, or dx. So that is just your distance over your time, right?
Yeah.
And you know your distance? It's the height, right? So then you know the height. Do you agree with me there?
The problem is that we have problems with our scale, so the time will do better.
Oh, no. But you can still calculate this time in theory.
Yeah, it's
Okay. So basically, what you end up with is square root 2gh for your velocity. Because this is the same sentence, okay? So because of that, actually, can you go to your slide where you show the height versus the peaks and the dips?
height versus peaks.
So it's probably about, oh, okay, yeah. Right, so, yeah. So you can see here it's kind of curved, right? I think that what you can do here is you can plot a square root fitting for your curve, and then you can see if it matches with your gravitational constant, and then you'll know that your theory is correct. Does that make sense? Okay. I think, let's move on to actually the effective parameters, since you didn't use the center of mass in your calculations. I think that's fine. Yeah. Could you go to the shape of the hourglass? Yeah.
You mean
The angle, the angle.
The angle.
Yes. So do you think the angle of repose that you use? Yeah. So do you think that there's any effect actually of this angle of repose on the?
Actually, when we measured the graphics, we saw that there was not.
Okay. Yeah, so I agree with you there because again, in your formula, there's really no term for the angle of repose, and the fact is really not that important. Yeah. Okay, that's good. Then regarding the density of your particles, so I noticed that you're changing the particle size as well.
Yeah.
And you think that the particle size doesn't really matter.
Because the difference is.
Okay, but then I think that if you change the particle size and comparison to the orifice, then your flow rate will also change.
Yeah, but.
So when you change the density, your flow rate will also definitely change. So how can you control so you're only changing the density and not changing the parameters?
Actually, there is not a big difference between our particle size, so we thought that there would be much more air entering between this material, so we thought it would be more homogeneous approximately.
Okay, but then the flow rate, so you never actually measure the flow rate for your objects? Okay, well in that case, I don't think that it's possible that you could say that by changing the density, you're not also changing the flow rate itself. Because if you do change the flow rate, then again, what you should see in the transfer conclusion, and that's the in mind. Okay. Can you show me the graphs where you look at the plateau part?
Which one? In fraction of this?
Yeah, so you expected the plateau okay, to be above zero, and it is slightly above zero here. And although this approach here is very simple, I don't think that this approach, which is also your approach, can actually explain this plateau part.
Actually, we thought that with that approach, just with the observation, if the material we put on the upper part of the hourglass, would reach at the orifice, then we wouldn't have seen such change. But since it was reached, so the height difference would be in favor of the particles which are observed first on the balance. The height would be high. But unfortunately, in the experiments, we would see clouds change in our other graphics.
So I think you do see that it is close though, right?
Yeah, but that's the only function lens.
Okay. And so your explanation for this is because the collisions will be greater than the amount of sand that's in the air.
Actually, the amount of sand transferred, so the raising by 20.
Okay. So actually, I think the explanation here is because the sand at the top is also moving and the sand at the bottom is also moving upwards. So that when these two are added together with the sand gliding to the bottom, then you will see that kind of an increase. And I don't know if you can tell here, but actually when you increase the density, the solid is also increased, right? Okay. I think we need to move on to talk about your experimental setup. So you used a digital scale, correct? Can you explain why you chose this digital scale and not?
Because we just have this digital
Yes,
scale.
I agree. So can you show the first graph that you did with the very first graph they showed the entire process?
Observation.
Yeah.
Actually, here these are nodes where we see the same thing.
Yeah, so I just want to clarify.
It's corresponds.
So what are you taking in your measurements? For your dip, do you take the minimum or what do you do to make your measurements? What are you measuring exactly?
Well, we take a video of the scale,
Yeah.
and then we enter time by time. We divide a second into 30 parts, and we just insert it.
Because you split your experiment into 3 parts. You have your drop, right? So what do you measure here for your drop? Your initial dip. What are you measuring? Which one is it? Minimum. And then here you measure always the transfer. Okay, and what about in the middle part then?
We were taking the average.
And okay, so, but how do you know when this begins and when this actually ends. I think it's...
Gets up, and here you can see that it's that.
Okay, well, I think that to prove this also, you can also look at the slopes over here. And perhaps if that matches with the acceleration again, then we would know that your experiment makes sense. I just want to ask you one more question. What do you think is the most important parameter in your experiment?
What we have seen was the height
The height of the... Okay.
of the sand.
Okay, and I agree with you there because obviously the height will change both the amount of sand that is in the air and also the maximum velocity when it flies in the bottom. That will obviously change both the minimum and the maximum. Okay, thank you. So to summarize the discussion with the reporter, the opponent talked about how exactly the scale measures the weight and suggested a simplification using their theory that could actually find the mass more clearly. However, we didn't have time to actually talk about the center of mass, which the opponent thinks can be used to explain why there is in fact the additional mass in the plateau section. And we clarified some of the relationships for the parameters, specifically regarding the flow rate and also the height. So for the height, we demonstrated that in fact the graph should be a square root curve, seeing as the velocity relationship to the height is also a square root relationship. And we clarified that the angle of the funnel is also not very important, seeing as it is not appeared in their theory. And then we also talked about how they can improve their experiment. First, regarding their changing density, they cannot change the particle size, seeing as this will also simultaneously change their flow rate. And they should use a better scale, perhaps a load cell would do fine. Thank you.
Thank you very much. Questions or reviewers?
To the reporter, do you believe that the flow rate, that the pressure from the upper container can be compared to the hydrostatic pressure
Pressure from?
from the upper container that comes downwards? Yes, or that's yes, no, not the air pressure, but the pressure that comes from the sand. Or let's just say draw a diagram where it says flow rate over time, please. Flow rate of the sand that comes from the upper part to the bottom part over time. Over time.
What we have seen in the experiments that we had, actually probably it was due to our release mechanism, we had at the beginning less particles than...
Okay, maybe the opponent wants to...
Right. So actually you can assume by Jansen's law that the flow rate is constant, and it's not really comparable to hydrostatic pressure, because once the height is above a certain threshold, then the pressure won't
So you
increase.
disagree with the report? Since
It should be a straight line if it's flow rate.
so it's not constant, okay.
It is constant. It is constant.
Yeah, but the report didn't say that it was constant, so
yeah.
disagree.
Yeah.
Okay, to the report again, you said that the upper peak increases with an increase of the total mass that is in the system. Don't you believe that when there's more total mass in the system, that also the lower container rises up, and therefore the distance gets lower, and therefore the upper peak should be lower and not higher?
Actually, but you're right, but what we have seen in our experiments was that the effective mass, more mass was our coming from effective mass.
But in your formula with the force, the height was in the like it was above the line, so that would say that it was increased. The force would increase with higher height, and I believe that this didn't make a lot of sense since the total mass increase would mean a lower height. Again, can all the system's behavior be explained by free fall to the reporter, since that wasn't pretty clear in the discussion? Can all the system's behaviors be explained by just using the free fall and the momentum transfer?
I don't know, but what we so that in our
To the opponents, would
You
you
can use
make-
momentum, but it's not entirely free fall because we know that the sand at the orifice does not start with zero velocity.
So what more could you use to?
So a better approach would be to just look at the center of mass.
Yes.
But of course they
I
didn't
agree.
do that.
Okay, thank you very much.
Thank you. Preparation.
The
Hello, ladies and gentlemen. My name is Martin, and I'm going to present the review on this topic discussion. First of all, to the reporter. What we found really good was that you visualized the whole phenomenon for a better understanding. Parts which we think that you could improve on were, first of all, the self-presentation, since you didn't speak very loud, and there were no slide numbers. In general, kind of an unstructured report. And also, the assumption of your theory were not mentioned at all, and they were not stated, and they were not proven in general. The measurement resolution we thought was too low, since it almost looked like discrete values in your experimental plots, and also the measurement range sometimes was too low. There was too less measurement points to define a peak in most of the parts, and also it was hard to follow the experiments since the parameter variation was shown very quickly. And you did not calculate any errors for your density measurements, so we believe that you should have done more investigations on to show the error. In terms of your opponent, we found that you asked really relevant questions. You clarified the non-understandable points, and you clarified the measuring method, we also thought was a big point of critique. Although he did partly present his own strategy, which of course is appropriate in some sense, but you shouldn't present your own strategy when you're trying to do your position, and did not invite the reporter to discussion really, but because he was so busy explaining his own strategy for the problem. He changed fast between his problems, and his theoretical approach, which he explained here, was without any derivation. I still believe that he should have done more discussion about the lack of measurement points, because we thought that this was a really big point of critique that we found, since peak cannot be defined by that few measurement points. During the discussion, they first talked about the theoretical approach, where the opponent stated that it could be improved by also taking the center of mass acceleration into account. And the reporter answered that the theoretical model for single particles, and I believe that she didn't really understand the question, and she didn't really answer the question properly. And we agreed to the opponent that definitely that theoretical approach could have been improved by also taking the center of mass into account. The next point, the shape of the hourglass was discussed, where the opponent asked whether the shape of the hourglass does make a difference. The reporter asked if it has an influence on the flow rate. We agreed to the opponent that the theory misses parameters and doesn't take that into account, and also that the experiments could have been more sophisticated in that matter. It was in the flow rate, which was influenced by the density point of the discussion. The reporter said that it gave an unclear answer, and the opponent then answered the question himself and said that the density does have an influence on the flow rate. And on the last point, which was the sediment experiments, the opponent also stated that the resolution was too low, and the reporter answered that he just wasn't in a position to use paper scales. We think that the setup should, first of all, be explained more detailedly, and second of all, she could have used better measurement methods in order to get better results. Generally, we believe that the task was not fulfilled, since there was no theory experiment comparison, and generally the theory did not really do anything in the report. And we still believe that the measurement resolution was one of the worst points in the report. So we believe that the task was not fulfilled. Thank you very much.
Thank you. Concluding remarks.
first are graphics which show the impact, the concept of the effects, and we do analysis and for that one, as I stated, that was what we have seen in our experiments. As it should have been considered due to our releasing mechanism. We have seen that as probably the reason of our errors, but overall, there have been talks about the errors, but we see that with the standards of our graphics, they are not very incorrect with the theory. We see that if it should decrease, it increases. If it should decrease, it decreases. So, and we thank to the other teams for their valuable remarks. So that's all for today.
Questions from you?
Short clarifying question to the reporter. Did you have any measurement repetitions, like for the same setup? And do you have an estimate, like roughly how much the peak height then changes? And if you repeat with the same conditions, how different the plot look like? For example, for the peaks.
We see a graph here, so like if we would make the same measurement, put that one like basically here, or could it be also here or somewhere here or something like that?
Well, it's didn't change very much.
So like 0.5 or how much?
0.
Half a gram, something like a lot here now. Okay, Farida?
How you calculate the velocity of one grain?
Yeah,
Because you use the sand.
Yeah.
So
So if
can
you show us the
can you show
formula,
your slide?
if you show us the formula, it was yeah. How will you calculate the velocity of 1 grain?
Actually, tried to calculate by dividing our video image by image, but we saw that the reaction time of our balance was not the same after each month, so measurements were not very accurate.
Okay, and if we already see this formula here, so once you can, because there was a question from the opponent, so this formula is for an elastic collision of the grains or inelastic collision of the grains? And it's the case, yeah? It's like it doesn't jump out or something.
Well, actually, for the jumps, we couldn't consider jumps because there are other particles who are only acid, and we couldn't in real life not any of the jumps function is elastic, so that is inelastic.
Can I comment on that?
Yeah.
I believe that generally speaking, when you look at the hourglass at the bottom half, it looks something like this, and therefore the collision is not inelastic at all, since it more decelerates when falling down here, and when like going down there. So I don't think that you can approximate it with inelastic.
I have a question. So they use the different material. For example, in their slide they have write down that there is an aquarium sand and then there is lantern. Do you think the surface of the like the shiny surface or the smooth surface of the grain vary your experiment with the different the shape, not the shape, but the surface of the smooth surface. Whether
Yeah,
we have
it
rough
would of course affect the friction that the grains have on each other, and therefore probably affect the flow rate. Yes.
Any other questions? If not, then thank you very much.